Hello viewers and my dear students. Welcome to session 2 on modal analysis, where we are doing a demo on modal analysis of cantilever beam. In the first session, we are totally concentrated on theoretical part, how to get the natural frequencies and all that by theoretical methods. I'll just brief you again what exactly I've done in the first session, and I'll come back to the answers. See here, I told you from the initial position, if it is subjected to displacement here, going from here to here and come to this position, this is one cycle. If it does one time in 1 second, it is called one cycle per second or 1 hertz. If it does 2 times in 1 second, it is 2 hertz. If it does 10 times, that is going from here to here, here, again coming to this initial position, if it does 10 times in 1 second, it is called 10 hertz, or multiply by 60, it will be 10 into 60, it is 600 rpm. These are all the basics what I have told you, and also I have told you in the previous session what is natural frequency. Okay, the unit of natural frequency is cycles per second or frequency in hertz, and I told you modal analysis also, where we determine the natural frequencies and mode shapes of the structure. Okay, any structure. Here we'll do natural frequencies of a cantilever beam. First natural frequencies, second, third, in that way, and we'll prove it by using Ansys also. And I told you what is resonance also. When the externally forced frequency matches with the natural frequency, resonance picks up and there will be a massive increase in amplitude of vibration, and the stresses will increase and the structure might collapse also. That's why if you do the modal analysis and if you find out the natural frequencies, that means to understand those natural frequencies, you are, as a designer, you are advising you should not operate at those natural frequencies. You can operate at any other frequency, but not at natural frequency. If the natural frequency is 800 rpm, don't operate at 800 rpm. You might operate much below 800 rpm or above 800 rpm. You avoid that 800 rpm if it is the first natural frequency. If it is second natural frequency is 1800 rpm, okay, don't operate at 1800. You operate less than 1800 rpm or more than 1800 rpm, because if you operate at 1800 rpm, resonance picks up and there will be a massive increase in amplitude of vibration. These things, massive increase in amplitude of vibration, resulting in massive stresses developed. As a result, the structure might collapse. That is why these things we will do it in the next chapter. That is, these are all the things, that is the concept of resonance and all that. We'll do it in the next chapter, that is harmonic analysis. Okay. Now we'll concentrate only on modal analysis, where we'll determine the natural frequencies. Okay. Now I have told you this is a simple beam, length 1 meter and breadth is 0.01 meter, 0.01 meter breadth and height 0.01. Okay, B and H. Okay, and modulus of velocity is so much, 2.068 into 10 to the power of 6, 2.068 into 10 to the power of 11 Newton per meter square. Density is 7830 kilogram per meter square. Okay, sorry, kilogram per meter cube. Sorry, 7830 kilogram per meter cube. Density is that. Okay, this is the thing. Now I'll tell you how to do this by theoretical methods. I told you this is the formula. This you get it in radian per second. If you want to get it in cycles per second or hertz, we'll divide by 2 pi. Okay, see here I told you lambda is the eigenvalue. The circular frequency is 2 pi f. F is equal to frequency in hertz. That is why in place of omega, I'll substitute. Okay, in place of omega, that is, if I divide by 2 pi, you are getting in hertz. See here, that is, F is frequency in hertz. That is omega by 2 pi. Okay, that is why whatever is that, I'll divide by 2 pi to get it in hertz. That is what, that is why 1.875 square, if you see here 1.877, if you do directly this way, you are getting in radian per second. Okay, if you do by 2 pi, divide by 2 pi, you get it in frequency in hertz. Okay, and multiply by 60, you get in rpm also. 1.875 square divided by 2 pi ei ml to the power of 4. This is E Young's modulus. that is whatever they are given, you feed it. I equal to BD cube by 12. Okay. M is mass per unit length, that is area of cross section. Okay. That is mass per density into area of cross section, mass per unit length. Okay. Rho BD, it is L to the power of 4. This I have told you. Okay. E BD cube by 12. Rho mass per unit length is this. Rho B into D L to the power of 4. If you simplify, it is E BD will get cancelled, BD square by 12 rho L to the power of 4. ED square by 12 rho L. This you remember. This will remain same. This, if you substitute, these are all constant, no? E will be constant, that is D square will be constant and all that, 0.01 square. Okay, this 12 is constant, 7830 is constant, 1 to the power of 4. This you will get 212.8 only. Okay, in that way, it is only here, first natural frequency, 1.875 square by 2 pi. Okay. This is into 212.8, 8.16 hertz or 489.7 RPM. This you have to prove it using Ansys. The same thing you should get, first natural frequency. Let us say second natural frequency, the formula is this, 4.694 square by 2 pi. This is anyway same, that you get 212.8 only. That if you do, it will be 51.15 hertz. And if you multiply by 60, this will be in RPM, 3069.3 RPM. Okay, this is in RPM. That means this is the second natural frequency. This is first natural frequency, 8.16. This is 51.15 hertz is the second natural frequency. This also you have to prove it in Ansys. The same thing you should get. Third natural frequency, same thing you do. 10.855 square by 2 pi, 212.8, 200 root of 212.8, 143.25 hertz. This is the third natural frequency. In the same way you can do, but at least remember how you are getting the three natural frequencies. At least these three natural frequencies. Anyway, we'll prove it using Ansys. Okay. Now you see here. We'll go to the Ansys now. Okay. Once you go to the Ansys, as usual you go File, Clear, Start New. Okay. These are all the initial things. Always you stick to this habit. Okay. But then File, change job name you do. Okay, I have told you. Do that. Modal analysis. Okay, this is create a new log and error files. Yes, you say. Okay, say. Okay, go to that modal analysis. Then file, change title is there. No? Here you do modal analysis of a cantilever beam. Okay, modal analysis of a cantilever beam you say. Okay, just fit you do. You get modal analysis of a cantilever beam, time, everything you get. And this is a new log file. Whatever we do, it will be stored here. As I told you earlier sessions and all that, it will be stored here. You can copy this in the log file. That is in the log file. Whatever we do using graphic user interface, no? Graphic user interface, all would have been recorded here. You can copy this and paste it in this Ansys command prompt and get the same answers. You can change the load, everything you can, whatever you want to make the changes, you can do it there and make the changes and analyze again. And I'll tell you in detail, okay, in the other chapters. Okay, this is the thing. Now you have changed the title and you have created a separate log file, go to that model. Okay, now you see here, carefully you do. Now you start from here, preferences, structural use. So initially, structural analysis has to be done and finally it has to be changed to modal analysis. First, okay you do. Okay, then you go for preprocessor, element type, add, edit, delete, add you do. Okay, beam 2 node 188, what you know already. Okay, beam 2 node 188 you take, just say okay. Okay, what you've done it in beams, no, the same element I'm choosing. Okay, just say close. Beam 188 element you choose. Okay, beam 188 element does not ask for real constant. Okay, did you follow? You need directly the properties of this. Okay, then you go for material properties, material models. Okay, structural, linear, elastic, isotropic you take. See here, whatever they are given, 2.068 E11 is the, let us say, is the Young's modulus. Okay, this is, I am doing it Newton per meter square. If it is Poisson's ratio is 0.3, 0.3 you take. If it is 0.27, you take 0.27. Okay, 0.27 you take. 2.068 e to the power of 11. This is, understand, Newton per meter square. That means the load should be Newton and the model should be in meter only. Okay, Newton meter square, consistency in the units should be maintained. Then say okay. Okay, but don't forget, in any of these modal analysis problem, density has to be put. Let us say 7,800 is the density. You put density also. Density 7,800 kilogram per meter cube. You kilogram per meter cube. That is why directly take. If it is in mm, you have to mm, you convert into that, you convert into 10 to the power of minus 9 and all that. Don't worry. It is, we are doing model in meter cube only, meter only. That is 7,800 is okay. Just say okay. Okay. Now this has been done. You have fit the material properties. Okay. You just say material exit. Okay. Then you go for section. Okay. Beam. Common sections you go. Okay. Common section if you go, you take the rectangular cross section. 0.01 you take. 0.01 you take. That is, width and height is 0.01, 0.01. As you know, you see the problem. The breadth is also 0.01. Height is also 0.01. You just say okay. Okay, once you do this, okay, then you go for modeling, create key points in active coordinate system. One you do, this is 0, 0, 0. Okay, you just say apply. Then you just say 2. And as you know, the length of the cantilever beam is 1 meter. It is 100 you put. Just say okay. Okay. Then create lines. Create lines. Straight line. Between this point and this point you take. Just say okay. Okay. Now I have taken this line. That is, I have created a line. And you know very well, it is fixed here. And it is free here. That is why it is a cantilever beam of length 1 meter. Okay, of length 1 meter. And it is fixed here. Anyway, we will do all this. Okay. Now, once you do this, you see here, meshing you go. Meshing. Mesh attributes, default attributes only you take. Because there is only one material, no different materials and all that. Just say okay, default materials. Now, size controls is important. Go for size controls. Manual size. Lines, picked lines, pick this line, just say okay, number of divisions you make it as 10. Okay, number of divisions you make it as 10. Now you get 10 lines. That means you finally it will be converted to 10 elements. Now mesh, lines, pick this. Okay, if you pick this, this has been converted into number of elements. Now you see here, list, elements. If you see here, 10 elements would have been created. Okay. Now you please understand. Now we have done this. Okay. Up till here, whether it is modal analysis or harmonic analysis, more or less the procedure is same till this. That is why what I'll do is I'll say save DB now. Please understand save DB. Now what I'll do is once I do resume, let us say I do this modal analysis completely, I'll get the answers and all that. Then if I say resume DB, it will come to this stage. Then whatever is required for harmonic analysis, you do. Okay. Now, did you follow? Now, this is, I have saved up till here. Up to meshing, I have saved. Now, we have come to the end of session 2 on demo on modal analysis of cantilever beam. Thanks, friends. Thank you very much for watching. Please look to my session 3 for further procedures in this session, further procedures in modal analysis of a cantilever beam. Thank you very much for watching. Thank you.